So thank you very much, Trevor, for the kind introduction. As he said, I'm currently a postdoctoral fellow at the University of São Paulo in Brazil. And today I will present a work addressing slabs under asymmetrical punching loads aided by linear elastic finite element analysis. This work was performed in collaboration with Professor Eva Lansot from Universidade São Francisco de Quito and TU Delft, and also with André Setiawan from Polytechnic School of Lausanne, and Professor Munir Debs, which is my main advisor. So we applied these methods mainly to one-way slabs under concentrated loads, which is a kind of loading frequently discussed on solid slab bridges, on which we have frequently the combination of several concentrated loads applied close to the support, close to line supports. But since it's not usual testing such as slabs until failure in real scale, we frequently discuss the problem on reduced scale experiments on which we apply a single concentrated load close to the support of these slabs. So some discussions assumes that this could simulate on a reduced scale the whole design crook applied on the bridge slabs, but it's more well accepted that this would simulate only one of the single concentrated loads from the design crooks in these slabs. One of the things that I think it's beautiful in this problem is that this kind of slabs may develop even one-way shear failure as wide beams due to the linear shear flow between the load and the supports. As well, these slabs may fail by punching shear if we look to the radial shear flow around the concentrated load. So one of the main purposes of this work was trying to clarify the existing methods using linear elastic finite element analysis together with the critical shear crack theory expressions. At this point, one of the first questions that frequently arises is how we use linear elastic analysis to predict the failure load of such slabs. So it's important to explain that we use the critical shear crack theory expressions to determine the governing failure loads, and the linear elastic analysis are a way to improve the estimation of inputted parameters needed in the critical shear crack theory expressions, such as the shear demand in specific control sections of the slab. The other motivation of this work was trying to improve the existing methods that combine linear elastic analysis with the critical shear crack theory expressions. If we work to these previously results, we can see the comparison between tested and predicted resistance using the one-way shear method and the punching shear method for the slabs that failed even by one-way shear or by punching shear. So if we look to the one-way shear method, we will see that the one-way shear method provides accurate values of resistance regardless the slabs failed by one-way shear as wide beams, which are the red points, or by punching shear as slab column connections, which are the black points. But in the case of the punching shear method, we realize that the method works fine only to the test that developed punching shear failure. In the case of the slabs that failed as wide beams in one-way shear, the predictions can be overly unsafe. So the one-way shear method that combines linear elastic analysis with the critical shear crack theory expressions is presented in detail in the thesis from Natario, from Lausanne. And the idea of the method is to use the linear elastic analysis to estimate the average shear demand and the maximum bending moments on one control section close to the load or to the support, depending on the boundary conditions. After, we took these two parameters estimated with the linear elastic analysis, and we put into a subroutine based on the critical shear crack theory expressions, on which we will vary the applied load until the estimated shear demand be equal to the estimated shear resistance. At the end, we will find both the unitary shear resistance as well as the concentrated load that causes the one-way shear failure. In the case of the punching shear method, the idea is more laborious, since we need to evaluate the contribution of each side of the conduct perimeter into the punching capacity. So we need to evaluate the distribution of the shear demand in each side of the control perimeter to determine the effective length of each side. After, we need to evaluate the distribution of bending moments in two sections crossing the load, to estimate the slab strip over which we will evaluate the bending moments. And at the end, we need to evaluate the distribution of bending moments at 4 sites crossing the load to estimate the control bending moments. This slide is only to illustrate all sections that we need to evaluate the bending moments and shear demand. In total, we have to evaluate 10 sections of the slabs to estimate the punching capacity. So it seems that... So after we calculated the effective portion of the control perimeter, the distances from the load to the point of 0 bending moments, and the control bending moments, we put these parameters into the subroutine based on the critical shear crack theory. So for each applied load, we will calculate the respective slab rotations of each side of the control perimeter, the corresponding shear resistance from each side, and at the end, we can calculate the total punching capacity around the load. In order to avoid the overestimations of the punching shear capacity, for the test that failed as wide beams in one-way shear, I proposed to apply a coefficient function of the relation between the slab width and the load size in the transverse direction in such a way to improve the estimations of the failure load. The idea is that as lower the slab width compared to the load size in the transverse direction, lower would be the contribution of the lateral sides of the control perimeter to the punching capacity. So now I'll speak a little bit about the simplified method that I proposed that doesn't need the use of linear elastic analysis. So in order to estimate the one-way shear capacity, we may assume the behavior of the slab as a beam loaded over the entire width, but with a width equal to the effective shear width. And the effective shear width needs to be corrected according to the load position in order to avoid overestimations of the predicted one-way shear capacity. In this way, we decrease the effective shear width as the distance from the load to the support increases. In the case of the punching shear method, without the use of the numerical models, we may replace the function of the slab rotations that was based on the relation between the bending moments, the acting and the resistance bending moment. We replace this expression as function of the slab flexor capacity. In this way, we use wheeled line analysis to estimate the slab flexor capacity, which simplifies a lot the calculations. And in this case, we also applied the coefficients related to the slab width to consider a lower contribution of the lateral sides of the control perimeter as function of the slab width. In the case of the numerical models used in the refined method, we used shell elements to simulate the slabs, and we applied the linear elastic material properties to these slabs in order to consider the concrete cracking in a simplified way. We decreased the concrete shear modulus in the simulations. We used a Poisson coefficient equal to 0 in order to improve the estimation of the shear demand and bending moments around the load. We tried to assure at least 8 elements along the load edges. The load was applied as a uniform pressure in the numerical models, and in order to simulate the free lifting between the slabs and the supports, we created solid parts to represent the support plates, and we applied an interface with free lifting between the supports and the slab. The database that I used in this study is the same used by Natário, which included 48 test results with simply supported slabs, but it includes tests with different shear failure mechanism, which means that some tests failed by one-way shear, while others failed by punching shear, including the tests from Damasceno, Ferreira, Regan Rezai Gerobi, and Karen Haysen. So these are the main results that I obtained, showing the comparison between tested and predicted resistances. In the first column, the predictions using the one-way shear predictions, one-way shear expressions. In the second column, the predictions using the punching shear expressions. And in the third column, combining the most conservative predictions between shear and punching shear expressions. In the first line, I show the predictions using only the simplified method without the numerical models. And in the second line, I show the results of the refined method combining linear elastic analysis with the critical shear crack theory expressions. We can see in figure A and B that the predictions between the one-way shear expressions and punching shear expressions reached a similar level of accuracy, regardless the test failed by one-way shear or by punching shear. And the average ratio between tested and predicted resistance varied between 1.06 and 1.14, with a coefficient of variation lower than 15%. In the case of the refined method, figures D and E, we can see that the predictions are also interesting in the terms of the average ratio between 1.1 and 1.2, with a coefficient of variation lower than 20%. But we can see that the scatter in the predictions with the punching shear expressions is still a little higher compared to the one-way shear method. So at the end, I concluded that the combination of linear elastic finite element analysis is a promising method, since it requires a lower number of semi-empirical factors in the approach, and because it also provides a better insight about the distribution of shear and bending moments in the interest regions. We also observed that the use of only analytical expressions can also achieve excellent levels of precision, considering the key parameters in the transition between one-way shear and punching shear, and that the transition of the governing failure mechanisms according to parameters such as the shear slenderness and the slab width to load size ratio can be reasonably captured with the proposed semi-empirical factors. So these are some of the references that I used in the presentation. Thank you very much for your attention. I'm open if you have any questions.